Hello, my name is Tolson Bell. I'll be presenting today on the sunflower problem, which is a challenging problem that lies in extremal and probabilistic combinatorics. Everything I present today is joint work with these two other co-authors listed here. If you're interested in more, the work I present today, we've written a paper on, which you can view here on arXiv. So to tell you about the sunflower problem, I need to define a combinatorial sunflower. So I want you to look at this picture on the right in green and red. These dots are the elements of the sets, and the ovals are the sets. The thing I want you to notice is that all of the dots are either in the very center, that is, in all of the sets, or they're in exactly one of the sets. In other words, there's no dot that's in only two of the sets, or in only three of the sets. So that's what a sunflower is. In other words, the intersection of any two sets is the exact same as the intersection of all of the sets. And we use K to denote the number of elements in each set. Usually we think of it as being a set system where each set has the same number of elements. And P being the number of sets that form our sunflower. So here's it written in more mathematical language on this side. The center of the sunflower we call the core. And then the remaining parts of each set, which are then disjoint, we call the petals of the sunflower. So P is then the number of petals. And one thing to note is that we don't specify the size of the core. So the core could even be the empty set. If we have P disjoint sets of size K, then that's also a sunflower with P petals. So in some ways, this is, a contrived combinatorial problem, but it actually does have a whole lot of uses. So this is a conference on algorithmic analysis. So here's ways this is useful to algorithmic analysis. Each one of these bullet points, there's been a paper written connecting sunflower to each of these. So these are not just theoretical possible applications, these are actual applications of the sunflower problem people have found. For instance, fast matrix multiplication, that's multiplying matrices in O of n squared time, right? That's one of the outstanding questions in theoretical computer science, and there's been papers relating the sunflower problem to that. So let me say formally what the sunflower problem actually is, okay? The idea is that if we had tons and tons of sets, eventually some P of them would form a sunflower. And if you think about this intuitively first, the idea is that either these sets will be very spread out over our universe of elements, in which case we can probably find P disjoint sets, or they'll be very overlapping, in which case maybe we can inductively take out some core and find some sets that form this nice sunflower shape. So the idea is if we have enough sets, we're guaranteed to have a sunflower. And the question is, how much is enough? Right? As a function of P, the number of petals we want, and K, the number of elements in each set, what's the R such that R to the K sets of size K guarantees a sunflower with P petals? And the reason we say R to the K, so this study was started by Erdős and Rado in 1960. They showed that if you have K factorial times P minus 1 to the K sets, then you always must have a sunflower. They also showed an example of P minus 1 to the power of K sets that does not have a sunflower. So we have this upper and lower bound on what this R is to guarantee a sunflower. If it's about P to the K, then we might not have a sunflower. If it's about pk to the k, then we're guaranteed to have a sunflower. So we have this upper bound of pk and this lower bound of p. So the goal is to find the true answer somewhere between them. And in fact, Erdős conjectured that the true answer is probably basically the lower bound. In fact, that we can eliminate this k term entirely and get only a function of p to guarantee a sunflower. This was a pretty important problem to him. He offered a $1,000 reward for a proof or disproof of it. But to this day, nobody's claimed that. And in fact, even more than that, until 2018, the best known upper bound on R was still basically linear in K. So we have this upper bound that's almost linear in K, this lower bound of this conjectured bound of no K dependency at all. So we want to go from linear in K to no K dependency at all. And so this turns out to be a really tough problem. And Erdős was kind of surprised how tough it was to find out. 20 years after posing it, he was surprised it hasn't been solved. And another 40 years late after that, it still hasn't. But recently, there has been some really exciting work on it. So in 2019, there was this breakthrough that basically lowered the upper bound from linear in K to logarithmic in K. Right? We're going for no K dependency at all, but we got from linear to basically log of K. So that's a big improvement. And this was a really impressive paper with some great techniques they came up with to do this. And so they were able to find that. Their research sparked a bunch of new interest in the sunflower problem and new papers building off their ideas. So Rao then used kind of different tools to get a slightly better bound, a different proof technique, but still, generally building off the framework of ALWZ. And then after that, these four other mathematicians improved one of the lemmas of ALWZ. They actually were using this framework to prove a different conjecture in graph theory, which they were able to solve. But then Rao was able to incorporate their improved lemma and get the sunflower bound down to p times log of pk, times some constant in front, but other than that, exactly p times log of pk. Terence Tao also had an interest in this problem, and he was able to tie this same bound, again with a slightly different proof technique. And he wrote that as an expository paper on his blog, and then he wrote another paper in harmonic analysis building off of sunflowers. So there's one more use of sunflowers. So that's how it stood when we approached this problem, the best upper bound being p log pk. Our improvement was that we improved from p log pk to p log k. So this isn't a crazily huge improvement, right? The thing is, we really still want to improve this log of k factor, right? That's the real hurdle. And so we didn't improve that. We just slightly improved the p dependency. But we also looked at some other things with the problem, and so we found that actually the Rao and Tao methods that had slightly improved the bound actually aren't needed for what we found for our improved bound. Though the improved lemma of fk, n, and p is needed. We also found that the main lemma, which I'll present in this presentation, is actually asymptotically sharp. And I think that's a pretty big result because it really shows that there really is a barrier to this p log k. It's going to be pretty hard to improve it. We're going to need a really different proof technique. And I'll also talk about this during this talk. So let me talk about the idea of how we would prove the sunflower conjecture, okay? So we introduced this definition R spread. If we're given a family of sets, this family might be R spread or it might not be R spread. The condition of being R spread, which means spread out enough, basically the idea is failing to be R spread, which means that there is such a set S that does not have this condition, right? That's exactly what you would need to do this sort of induction, where you take out the core and then inductively find a sunflower and then add that core back in. This definition R spread is exactly what we would want in order to do that. And so what we want to then show is if a set system is R spread, then it has p disjoint sets. And then that's enough to prove the sunflower problem for that value of R. Because then, if it's R spread, we have p disjoint sets, which is a sunflower with p petals. If it's not R spread, then we can inductively take out that witness set S, find a sunflower, add that set S back in, and then that gives a sunflower on this original set system. So it's a slight twist on the induction. Maybe you need to think about that for a minute to get it. But that's how we can reduce this problem of finding this complicated structure of a sunflower. Now we just reduce it to a problem of finding p disjoint sets. So given this definition of a family being spread out, we want to prove that it has p disjoint sets, as long as it's spread out for some sufficient R. Right? So how do we find p disjoint sets given this spread out family? So what's a way to find p disjoint sets in a set system? That's what we're going to say here. Okay. So we have this universe X of all of our elements and all of the sets, whatever. That's the universe of elements. And imagine throwing each element into a random bucket, 1 through p. Okay, you get these p buckets. Each element is in one uniformly at random. The idea is that we're going to use the probabilistic method on this. Okay, and we want to find in each bucket if we can find a set in our family that got entirely thrown into that bucket. Okay? If each bucket has a set in our family entirely thrown into it, then that would be p-disjoint sets. Because each set is entirely in a bucket, the buckets are disjoint, and that's p-disjoint sets. So what we want to show is, given any one bucket, let's just look at one bucket now, the probability of it failing to contain a set, this is kind of our failure probability when we randomly throw it out, is less than 1 over p. Okay? And so because then that tells us if we do this p times, our overall failure probability by a union bound is less than 1. The probabilistic method then says if some random probability, some random partition into p sets has a less than 1 chance of failing, that means it has some probability of success. Therefore, there's some partition into p sets for which we have a set in our family in each set. And so then our family will have p sets. Now, of course, this showing that the failure probability for one bucket is less than 1 over p is also quite hard, right? But now we've reduced even further. Instead of trying to find p-disjoint sets, we're instead just taking a random 1 over p fraction of our elements and wanting to show that it has less than 1 over p chance of not entirely containing a set in our family. In other words, with pretty high probability, some set in our family is entirely contained within it. And so that's really, a hard thing to show, right? And so this is the main lemma that shows it. And of course, proving this is really hard. Again, analysis of algorithms, how this lemma is proved is actually an algorithmic argument. It's this nibble argument. We slowly grow this set until it gets to 1 over p of the total size, and we analyze the probability of failure at each set. So we analyze that algorithm. So that's another way this ties in. But basically, this lemma is exactly what we need. For this c, for this r now, we choose to be p log pk, right? For that r, Rao was able to prove that the probability of failure is less than 1 over p, given that we're taking 1/p of the elements. And this is the lemma that we proved was asymptotically sharp. Actually, we can't get a lower value of r than p log pk times some constant. So if that lemma is sharp, it's already like, well, if this is already sharp, how did we get an improvement over p log pk, right? So what we noted about this is kind of p is playing two different roles here. P is the fraction of the elements we take into this special set x sub p. Okay, p is also what we want the failure probability to be, 1 over p. And of course, that has to be, the same for it to work out to be less than 1 overall. But really, we can state the lemma in a bit more generality. Okay, let's put we select 1 over a, each element with probability 1 over a, and we want our failure probability to be less than 1 over b. Okay, then our bound is a log bk, and that's asymptotically sharp in a, b, and k. But then here's what we can do. Before, we split into p sets. The thing with that is we needed every single one of them to succeed in order to have p disjoint sets, right? For our improvement, what if we took 2 p sets instead? We split into twice as many sets as we need, okay? Now, only half of them need to succeed. Instead of every one of them needing to succeed, as long as half of them entirely contain some set in our family, then we have p disjoint sets. And so now we only need our failure probability to be 1/2 instead of 1 over p. Because then, on average, we'd expect at least p of them to succeed. And so then again, by a bit slightly different use of the probabilistic method, that means at least there must be some partition in which at least p of them succeed. And then that shows that there's p disjoint sets in our family. So then we use b being 2, our failure probability only being 1/2. We double a, but that doesn't change the asymptotics, and then we end up with p log k as our bound. So that was our improved bound. The proof isn't too long. I mean, maybe I went over it too fast to get it on first go through, but it's short to write out. But it was a nice improvement, and we were happy to get that. So I'll just talk broadly then about the state of the problem, right? So we have this problem, the sunflower problem, that turns out to be really useful in fast matrix multiplication and other things. And you can look at those papers. We try to figure out what's the R such that R to the K sets guarantees a sunflower. Erdős and Rado showed that it has to be between PK and P. Alois, Lovett, Wu, and Zhang lowered it from pk to p cubed log k. It got down then to p log pk, and a bit lower down to p log k. Okay? And we also showed that this main lemma is sharp, and so it's going to be hard to improve past p log k. But Alois, Lovett, Wu, and Zhang had a really good breakthrough, and there might be other ways to apply their ideas. Maybe there's other ways to apply entirely different ideas. I mean, we looked at this from a pretty probabilistic perspective, right? Probabilistic combinatorics, these random partitions. Maybe there's some other tools, enumerative combinatorics, maybe analytic combinatorics, looking at some functions, generating. I think there's a lot of ways this really important problem could still be improved. So we've shown some barriers, we've shown some improvements, and I encourage you to look at this problem for more. So thank you for listening. If you have any more questions, you can email me or any of my co-authors and read our paper on arXiv. Thank you.